So welcome back, and if you're new, welcome. Today, so we've already had two meetups so far, and despite the fact that this is called a computational biology reading group, we haven't actually done any computational biology. So that's going to change today. We're going to start our journey with RNA-Seq analysis. And actually, thankfully, there are just a few slides today. It's mostly coding. Um, but before we actually go through some of these slides, I'd like to get you to just go ahead and open the required R Markdown file for today. And that's because it will likely have code for packages that you don't already have installed. And I tried this yesterday on a different machine, and it took a few minutes to install. So hopefully that was just particular to that machine. But so we'll go ahead and start the download process, and then we can go back to the slides. So just as a reminder, if you have a project already open, set up for this meetup, that's great. Just go into your project. So I'm in this project, which I've called CBRG_meetups. But if not, that's okay. It's preferable to be in a projects environment, though. I should say, any questions from last week or questions in general? While you think about that, so we can go remotes. Remember, don't use dev tools because it's problematic for some people. We do remotes_GitHub. And now for this, you can either type what you've been typing before, or you can type this first. So the package has been moved to a different GitHub page or account called Duke CCT. So you can run this, or you can stick with the old one that's from my account. They're the same thing. So let's go with the Duke CCT. And the name of the package, oops. And then remember to set false equals true. So again, what we're doing here is, since last week and today, some updates have been made to the package. And we'll be replacing the package you already have, the version you have, by running this line of code. Hopefully you have no problems with this. And if you do, please let me know. Once you have this installed, you can just run the package by typing in library cbrg, and that's fine. And we can go ahead and launch today's project. We're doing launch project, and then it's 3 because this is meetup 3. Oh dear. Okay, it's there. And so you can see that the setup chunk this time is a little busy today, and that's because we're installing this package called DE-Seq2, which is this package, very popular package that we use for RNA-Seq analysis. And we're also installing this other package that's associated with one of the 2 books that we're following. And that contains a nice toy RNA-Seq data set that we will use today. So this is a nice function in a for loop that Paul wrote, keep everything neat. So you can just go ahead and run all of this. And keep an eye on your console, because R might ask you for something. So yeah, like it's going to ask you if you want to update. Just go ahead and update everything. So just do A, and then I'll continue to go through all of this. And if you have any issues with this, please let me know. This is always the most, so whenever it asks you for anything, just agree with it. This might be the most error-prone part of today. And if there are things that we can't solve right now, that's okay. Just please follow along. But these, like having DE-Seq2 on your machine's really useful. So if there's any pain points, it's worth addressing them. And as you can see, it's doing tons of stuff. So it's a little tricky because at some point it might ask you for another question. So what we'll do is we'll toggle back and forth between the slides. Hopefully it won't get too confusing. So today,
I'm sorry. I'm not getting the very first thing you did, where you get it off from GitHub.
Yeah. Sure. So what I'm going to do is just going to put that code. It's not responding. So let me just take a look.
Sorry.
No problem. people can watch it install.
Just here.
That is
I don't want to talk last time, so I think this fine.
Yeah, this seems like a okay. So it could be because you don't have this might be an issue. I'm sorry.
No, that's okay.
So did you just basically run the first chunk of code?
Yes. Yeah.
Did you have to, should we take away the hashtag from the install.package?
That's a good point. So actually, you should. Yeah. And the function that Paul wrote, and Paul, please correct me. It detects if you have the stuff those required packages installed, and if you don't, you'll get an error message. Is that correct? So yeah, good point. You can just uncomment that. So hopefully, almost everyone has these packages loaded, and we can just leave this as is right now. And again, if there are any issues, please let me know. All right, so RNA-Seq analysis. And so this is just a really quick one-page, one-slide intro to RNA-Seq analysis that I took from Wikipedia. And it has it nicely conveys kind of what happens in vivo. You go from, this shows transcription and formation of mature RNA transcripts, which is messenger RNAs that we're interested in. And the in vitro part involves taking these transcripts and breaking them down into smaller, manageable fragments, performing reverse transcription to get these stable cDNAs, and then sequencing those fragments, aligning them to a reference genome, and then getting these counts for each gene. And we can either look at, one of the things we can do is differential gene expression analysis, which is what we'll do today, or we can do more advanced things like detect levels of splice variants. That's a lot. And we will actually be skipping a lot of the pre-processing steps. So to go from the machine to to go from the raw sequences to doing quality control, to aligning them, and all of that. What we will begin with are the count data. So these are the raw counts for each gene. And the steps that lead this are also interesting and is something that we can revisit at a later point, but I think this is the more interesting part. And oftentimes you will get data in count form from a core facility. So I think this is a good place to start. I should say quickly that the DE-Seq2 package that we'll be using today is installed or can be found in this repository called Bioconductor. And Bioconductor is really a one-stop shop for computational biology. And coincidentally, fun fact is one of its originators is also one of the creators of R, Robert Gentleman. So R is baked into Bioconductor. So being good or knowing how to use R is kind of the Rosetta Stone for using Bioconductor. And in addition to having all of these packages, Bioconductor has these really nice courses. And I think the single most useful resource for me, at least, are these package vignettes. DE-Seq2 has a couple of really nice ones. So Bioconductor is where you want to go. All right. So let's begin. So if we go to the next chunk with the one that's marked load data. So these two lines, I won't really go into the details of them. I've written down what they do, but really they are, so at this point, let's run things line by line. So if we run the code on lines 42 and 43, so one way is to just go to the end of that line and hit Command Enter if you have a Mac. Sure. Hopefully this doesn't break things. Oh, I see.
Should there be a reason why when we run some of these lines, we don't get as much info in the console as you're getting? Should we be seeing all of the?
Are you getting any error messages?
No, it's just not showing like all these lines.
I'm not really sure why.
Okay, all right.
I would say that's actually preferable to seeing all of this stuff. So if you just go to the end of line 43, you can load the first data set. And if you go similarly, and that worked, as you can see here, I didn't get an error message. And if you go to the end of line 45 and do the same thing, Control Enter, you load the second data set. And if you look up here in your environment pane, you see that you have now two data frames. One is called cold data, and the other is called count. So let's explore these two data frames. So it says here that on line 48 that cold data is a small data frame. So when you have a small data frame, really the easiest way to see what's in it, the easiest way is to just click on it. And you can see here that there are 6 samples. And we have 3 columns. The cell information and type information in this particular case aren't especially informative because they're the same for everything. But what is really important here is this condition column. So it tells us that in this experiment, there were 3 members of the mock group and 3 members of the KD or knockdown group. I've gone through the book and I think they just, I know this is just toy data, but I don't think they actually say what was knocked down. So just imagine your favorite gene was knocked down in these cells. And so that's all that cold data is. So on line 41, if you want to write down what you should write down, you can just type in cold data. And if you just run that, we can see the contents. If we look at counts, on the other hand, it's a much larger object. And how do we see how big it is? Like, what function could we run to quickly get a sense of that? You could do glimpse, you could do dim. Let's try dim. And so we see that it has 58,735 rows and 6 columns. Now, if you wanted to actually see some of these things, one very useful function is this head function. And if we do head counts, we can see that these are the 6 columns and these are the first 6 rows. And all of the numbers in this, these are all count data. And if you were to see the whole data set, you would see most of these count data are just zeros. Nothing's detected. Now, if you compare counts with cold data, what do you see? Or like, what's the relationship between these two objects? So crucially for DE-Seq2, when we're looking at these input data, we can input lots of different data frames, but these are the kind of 2 minimum. We have to have these 2 data frames to be able to do our analysis. So the cold data, the counts data has our, as it says, count data. The cold data has information about the experiment. So if you compare these 2, cold data and counts data, you will notice that the number of columns of the counts data frame is equal to the number of rows of the cold data frame. And this is important because for every column in the counts data frame, there has to be a corresponding row with corresponding information about that column. Right, and that's really all there is for these 2 pieces of data. We can use, so now we move on to the DE-Seq package itself. And from the DE-Seq package, we have this gigantic function named DE-Seq data set from matrix. And what it does is it takes these 2 inputs. And like I said, you can also have additional input. For example, you could have a data frame that contains metadata, like who did the experiment, what machine was the experiment done on, and things like that. In this case, we just have these 2, count data and cold data. We have a third argument in this function called design. And rather than explain what design does now, I'm going to punt and save that for later on. So we just have this function with these three inputs, and we save it as an object called DDS. And it tells you that it did a couple of things, and it made this DDS object. Now, to see what this object is, we can just type in DDS and run it. And if we look at the console, we get something that looks should look foreign if you have no experience with these objects. This is not a data frame. This isn't a vector. This isn't a matrix. It is a completely different type of object. And if you just run its name, you get some information, but it isn't super useful. If you look at the new DDS object, so one way to do that is to just click on it, you see that it's actually quite complex. It's certainly a lot more. It's got, for one thing, unlike a data frame where what you see is what you get, here you have a lot of hidden information. If you click on the play button there, you can kind of see what's in it. Now, in this case, most of these things have nothing in them. They're just there. So this DDS object type, it has the capacity for storing additional information. Like, for example, I mentioned metadata. In our case, we don't really have any, so this is empty. So this is what's known as an S4 object, and I'm not really going to go too deeply into what this is. It's literally an advanced R concept. It's in the book. There's a book called Advanced R, and one whole chapter is dedicated to this. Briefly, an S4 object is an object that allows you to store complex data in a way that will make life eventually easier. Initially, there's a headache of trying to decipher what this means, but from a data analysis perspective, these S4 objects make life easy. So an S4 object has what are known as, so these different lines that you see here, these are called slots. And to see what is in a slot, a given slot, we use a new operator, this at operator. So for example, if you wanted to see what was in cold data, so that's this data frame here. If you wanted to see it in this new DDS object you created, you do DDS call at data. If we run this, we get the same output as this. Now, I'm going to skip this question here. I asked to see, all right, sorry, this should go here. And if you, so the problem with this is if you just use these at symbols to try to extract information out of this object, it can get a little bit confusing. And I'm going to skip the one where you get the counts data. There isn't a particularly obvious way of getting it. However, thankfully, there are functions that are intuitive and allow you to access this information in an easy way. So for example, if you wanted to see the count data that is now in this DDS object, there's a conveniently named counts function. If you just run that, you continue your console, you get the same counts data as the one you put in. And similarly, there's a function called assay that does the same thing. And if you wanted to see the cold data, instead of using that weird at symbol, you can just use the function cold data. All right. Now, that's all fine. To kind of show you why this is a useful object type, besides the fact that you have to have this kind of object, like you have to have this DDS object to do anything downstream using the DE-Seq2 package, is we can subset this package. We can subset this object to exclude some kind of information. So for example, let's say, so in this case, we have 6 samples, 3 mock and 3 knockdown samples. Let's say for whatever reason, I wanted to create a new object that only contains information that corresponds to the mock samples. So I can call it like DDS mock. And the way to subset is a little tricky. It's again using our notation, these square brackets, but it's not super initially obvious how to do this. And the point of this little exercise is not to show you how to do this subsetting, but show you what happens after. So I've subsetted this data so that now I have a new object called DDS mock that only contains mock information. And to confirm that, I can again use this call data function. You see now we only have this. And if I use the count function on this set, again, I only have count data for the mock samples. Now, why is this important? Let's say you had a sample that didn't pass quality control and you wanted to exclude it. In this case, we have at least two different separate data frames. If you didn't have them in this convenient S4 object, you would have to keep track of that information across all the data frames or Excel sheets or whatever you're using. And that's super error prone. Whereas here, if I say I don't want sample 5, I can just remove it from this S4 object and all information related to sample 5 disappears. So this is a very convenient and problem-free way of packaging this kind of complex omics data. And this DDS object, so actually we can see, actually there was a question earlier, like how do we see what this function does? How do we see what a function does?
Question mark?
Question mark. So we can do that and then just put the function name without the parentheses. And you see here, it gives you all the information you could possibly want and maybe not want about what this object is. And it tells you that it is a subclass of another object, which is in turn a subclass of another object called summarized experiment. And so summarized experiment is this object that is particular to, in this case, is particularly useful for RNA-Seq data. There are similar objects that you would use for metabolomics data or proteomics data, and they have different names. There's even an object that you can use for multi-omics data, and we will encounter these different kinds of objects as we move on. But the logic that you apply to this, that is applied to this, applies to those objects also. So becoming familiar with this this DE-Seq data set object or the summarized experiment object is a really useful thing. And in the quote-unquote homework for today, you will have a chance to practice this. Okay. So I have a function. I have a question here. Using functions from the tidyverse package on DDS, plot the counts distribution of sample 1. So just as a hint, to extract the count matrix from this DDS object, we do count DDS. We run that, we can see we have this here. So we use this as input to ggplot. Oh, well, actually, it's at sample 1. So we first select sample 1. And I can just do sample 1 again. What geome would I use if I wanted to look at a distribution? I can use a couple. I'm going to go with geome histogram. And I see that there are some. So this is something that is slightly painful, but is what trying to figure out why it's painful and problematic is the counts DDS object is not a data frame, and we have to have a data frame to use tidyverse. So one quick trick you can do is use this function called as_tibble. That should fix things. You get not the world's best plot, but you get this histogram for your counts data. And one thing you can see with the count data is most of it is 0. So count data, unlike data to do with height or weight, is not normally distributed. And this is something that affects the statistics downstream. We won't really go into that in too much detail, but this is nice to know. And I have a couple of other questions here that we can revisit if we have time, but I'll just move on. So that's this DE-Seq dataset object is what we need as step 1 to do the analysis. Now, I spent 27 minutes going over this. It's kind of embarrassing how easy it is to do differential expression analysis in DE-Seq 2. Because as long as you have the data in the right form, this raw count data, all you have to do is run this function called DE-Seq. And you can override your DDS object. And if you look at the console, it'll show you that it's actually doing a ton of stuff. So I think there's a saying that a function should do one thing, but do it well. This function seems to do lots of things, but it is doing a lot of things well. And there are lots of, so line by line, it shows you what it's doing. And this first line where it says it's estimating size factors. If we go back to the slide. Okay, so this is the DE-Seq 2 pipeline. So we start off with this count matrix, and these are the steps that we go through. And actually, all of these steps from normalization to statistical test were all done using this DE-Seq function. So that first step of calculating these estimating size factors, that is necessary for doing normalization. And so when you have raw count data, there are a couple of reasons why you would want to normalize. For one thing, it could just be that you have more reads in general for one sample compared to the other. And so you need to take that into account. So that's one thing, one thing to take into account. And the second one is this: you could have heterogeneity in the RNA transcripts you have. So in this case, for example, in control, you might have gene 3 that's not expressed at all. And in another case, you treat it with something and then it's significantly overexpressed. But there's no change in gene 1 or gene 2. And so if you just take into account total read amount and normalize to that, it will artificially look like gene 1 and gene 2 are getting suppressed. Their expression's getting suppressed. All of these are normalization. So DE-Seq 2 does a few different, the normalization steps, the normalization process involves a few different steps. And the paper explains what these steps are really well. But rather than get into the technical details, it performs this normalization for you. One thing worth bringing up is there are many different ways to normalize count data, TPM, CPM, so on. Unfortunately, a lot of those already normalized data cannot be used as input for DE-Seq 2. You will get it, the package and paper even warn you that you will not get proper you will not get a sensible output. And so it's critical when using the DE-Seq 2 package to begin with unnormalized raw count data. So that's the size factors, estimation of these size factors contributes to this normalization process. There's a second step, estimating dispersions. Again, this is something I won't really get into because it's quite a bit, but really the reason you do this, you estimate these dispersions per gene, is to work out eventually the standard error associated with each gene. And that's important for the statistical test that will be done later on. Same thing, gene-wise dispersion estimates, mean dispersion relationship, and then it fits the model and it tests it. So now comes the fun part, the looking at the output. And to see the output of all of this, all of these 6 lines, is you just type in results. We see here that we get this nice output where for each gene, we have a few columns. So this base mean is just refers to the average normalized count data across your samples for each gene. And this is a good diagnostic, I guess, column to look at, because if you have really low levels, then that means that across the samples, you didn't really have much. So if you get a significant difference, or quote unquote significant difference, and your base mean is really low, it's probably noise. Log2 fold change is self-explanatory. That's generally the thing that people are most interested in. So positive means increase, negative means decrease. And then you have this log fold change standard error. So this is that dispersion estimate I was talking about. And again, this by itself is not hugely useful, but it is used to work out the statistics. And so these are the statistics that you can use as input for, let's say, gene set enrichment analysis or something like that. And then we have the p-values, and we have adjusted p-values because we're accounting for multiple comparisons. So that's really it from start to finish. So if you have this unnormalized count data, you want to get fold changes and statistics, it's just like 2 or 3 lines. I'm going to pause here. Are there any questions about any of this? Okay, so one thing is, if you notice here, it says that when it's, the comparison here is mock, it says condition mock versus KD. Typically, that's not what you want. You want the other way around. You want your treatment or your KD versus your control or your mock. And one way to try to understand why this is the case, we can look at this condition column. To do that, we can just do DDS $ condition. If we run that, we see this thing here. So this tells us that condition is what's known as a factor. So that's a categorical variable with levels. And so what that means is this factor variable has 2 levels in this case. And the levels part determines the direction, or like how the statistical comparison is made. So what this means is the first level, KD, is the reference. And mock becomes a thing you compare it to. And we want it to be the other way around. So there are a few ways of quote unquote fixing this. One really elegant way is you don't change the analysis. So you have your DDS object as it is. But what you do change is this thing known as a contrast. And that's a thing that specifies what kind of comparison you want to make. So we just do contrast is equal to, and then we use this concatenate, combine function to create this vector here. And so what this takes is the name of the appropriate variable, so that's condition in this case. And condition comes all the way from our original Cole data set. So that condition, and then we put the one we want to, we put our reference at the end and the one we want to compare it to in the middle. So if we run this, we just look at res, we see now that the test was performed on the knockdown versus mock. So it's really easy to switch this if this is problematic. And so that's another thing when you look at the output, please definitely note this, because you might inadvertently be doing things the other way around. And then this is a nice little function, a line here, so it's as underscore Tibble, to convert this res object into a nice data frame. So we have to specify in this case row names equal whatever. In this case, we're calling it ensemble. If we don't do this, we'll get our results table without any of the gene names. So that's obviously not desirable. And if we look at resdf, again, this is our output. I have a few lines here about missing data. And the reason we have that is like a lot of these, like for example, like I mentioned at the start that a lot of the genes have count values that are 0 across all the samples. So if you have just zeros across all samples, there's nothing to compare. So you'll just get NAs for them. And that's actually quite a common feature. And I believe DE-Seq2 has its own, it makes its own additional decisions about what comparisons to kind of throw out because they're not really meaningful. So even for those, you will get a lot of NAs in your, especially your adjusted p-values. And so that's obviously problematic and something useful to get rid of. And so there's a nice function here called is.na. And to see kind of like, do you have any NAs? So missing values, you can do is.na and then apply that to a column of interest. So let's say adjusted p-values. And if we run that as is, so I take it back. By itself, it's not super useful. It just gives you a bunch of trues and falses depending on whether or not there's an NA. But you can use this function in conjunction with other functions to do something more useful. So let's say we wanted this res underscore df data frame, but with no NAs in the p-adjusted column. What could we do for that? So let's say I call it res no NA. Filter. How, using this filter, what would I put in the filter function to get rid of NAs in the rows that have NAs in the p-adjusted column? So we can kind of, so line 140 is a clue. So one thing about, sorry, I keep jumping in. Does anyone have an answer or a suggestion? So I pointed out that on line 140, when you run this function, you get a bunch of trues and falses. Filter works on, if you recall from 2 weeks ago, filter works on some kind of logical operation. Logical operations typically give us a true or a false. And for all the operations or comparisons that produce a true, filter will those rows, the corresponding rows, and all the ones that are false, filter will throw them out. So this already gives us trues and falses. So we can just copy paste it into this. Oops, not the right copy. We can just take this and copy paste it into our filter body. We run it. I'm actually kind of surprised that that worked. So this thing here, and this is specific to dplyr functions, you don't actually need to specify where p-adjusted is coming from. You can just do it like this. I'm just going to do it the correct way. And now if you look at the resulting data frame, oh, I did the opposite. So I'm just getting all the ones that are missing because that's what is.na is. It tells you, it gives you a true if there's something missing. So what you want is the opposite. The opposite of false. To get the opposite of false, you just put an exclamation mark before. And so it'll give you all the ones that are not missing. So we run this and look at the resulting data frame. We see p-adjusted, everything is there, is non-missing. Just in the interest of showing you another useful function, we could use filter and this is.na and all of that, but there's a nice function. So typically when you see people doing stuff like this, when I do stuff like this, inevitably someone has come up with a clever function to avoid doing all of this. And that clever function in this case is called drop NA. And you can specify, again, which column you want to drop your missing values from. You get the same output, which you can confirm. And it's just cleaner to do it that way. Now, one more kind of useful thing, and these are just like not really related specifically to RNA-Seq, but are just useful things that I do all the time. I thought I would share them. One way to confirm that what I did was right, like this drop NA function is actually doing what it says it does, is you can again do is.na on the p-adjusted column. And what you can do is you can just sum it all up. And this is kind of a weird thing if you've never seen it, like what is true plus true, what is true plus false. In R, all true values are coerced to 1. Well, a true is coerced to a 1, and a false is coerced to a 0. So if you have 5 trues and you put those 5 trues in the sum function, you will get 5. If you put a million falses, you'll get 0. So in this case, if I do sum, oops, sorry, wrong data frame. So to make sure that I'm doing things correctly, this is a nice thing, especially when you're dropping stuff, just to confirm to yourself that you have in fact got rid of all the NAs. This is a nice little thing to do, kind of sanity check. Yeah, so that's really it for RNA-Seq, starting with count data to get to up to this point, this res-nona data frame. And next week, what we're going to do is we're going to show you how to look at useful diagnostic plots. So I took a lot of things on faith here that you really shouldn't. But unfortunately, with analysis in general, it's critical to see if like certain diagnostic plots are giving you what they're supposed to give you. It's useful to do, for example, PCA and other such useful data visualization approaches. And we'll show you how to do that on the same data set next week. And Paul he's developed an app that is specifically designed to work with count data, so any kind of count data, not just RNA-Seq, and he'll give us a tour of it. And so that's a shiny interface, so you can just upload your data set and do things a lot more quickly and easily than you can in R. So that's really it for today. I have a little bit of quote-unquote bonus material for the stats fans. But before I move on to that bit, does anyone have any questions?
How can you import gene names to match it with the ensemble number?
Great question. So that's something we'll go over either next week or the week after. There are specific packages. So the question was, so if we look at this, res-nona, we see all of these ensemble IDs. And unless you're a robot, it's impossible to know which gene a particular ensemble ID corresponds to. Fortunately, there are packages within Bioconductor itself that allow you to not just convert this to common gene names, but to IDs that are used by other databases. So that's something we'll definitely look at.
And actually, are those packages constantly updated?
Yes.
Those things change.
Constantly, yeah, which is why Bioconductor has a reputation for being reliable. But yeah, in the package documentation itself, if you go to Bioconductor, it'll tell you what version it is, and there's always a PDF associated with it, and there'll be a date. So the packages on Bioconductor are kind of like packages on CRAN, very high bar of entry, so they're usually run by responsible people. Right. I wanted to end by talking. So another thing that I glossed over was this statistical analysis that's done. I thought I would take a couple of steps back and just introduce how linear regression, introduce linear regression itself, why we should care about it, and how to do it in R. So when people think of linear regression, they typically think of this. You are performing this regression. So people typically, or at least I think of simple linear regression where you have two variables. You have the variable you want to predict, and you have your input variable. And they're both continuous. So in this case, so this is a plot from last week, where in this case, we're plotting the mass. It's kind of hard to see, but we're plotting the mass of proteins against their length. And these are data that we got from Uniprot. And you can see, unsurprisingly, there's this nice positive relationship between these two variables. So for linear regression, people do linear regression for various reasons. If you're into machine learning, you probably do it because you want to predict something. And the way to predict something using linear regression is to take these data points and fit a line a straight line that best captures the relationship between these two variables. And what that means is drawing a straight line that is as close to the dots as possible. And when you do that, your simple model will have two resulting what are known as parameters. One is an intercept term. So that's that beta, formerly known as beta naught or beta 0. And that's the bit here where the line intersects with the y-axis. A lot of times that is by itself meaningless because that is the value of the mass when the length is 0. And so if it has any value that isn't 0, it doesn't make sense. But we still have it. And then the second parameter is this beta 1, which is the slope. So the resulting kind of formula is mass is approximately equal to the intercept plus the slope times length. And so that's the prediction machine learning part. The statistics part which is the one we're specifically interested in with the analysis we just did, is to perform stats. You can perform stats on both of these parameters, but the beta 1 is generally the more interesting one. And the question you asked there, the null hypothesis is beta 1 is equal to 0, meaning that there is no relationship between these two variables. So what you end up doing is you end up doing a t-test for this to ask whether this beta 1 term, whatever it ends up being, is it significantly different from 0? So keeping that in mind, things that when people think of, one thing about linear regression that people maybe don't think about that much is that you can do linear regression on categorical variables. So in this case, what we're trying to predict is continuous, but our input is not. Our input has just two categories. So in this case, it's obviously made up data. So I have condition, we have 3 controlled, 3 tested, and reading, whatever that means. We have 3 values of reading, 3 values of 3 values for control, 3 values for treated. Now, if you were to do this, if these were data that you generated, you would very likely just do a t-test and not worry about regression. The thing about doing linear regression on categorical data is it is exactly the same as doing a t-test. And so in that case, we have the same relationship. We have, in this case, our outcome, which is reading, is approximately equal to our intercept, which is weird because in this case, the intercept takes on an interesting alternative meaning, and that beta naught intercept term corresponds to the mean of your control group. And the beta 1, the slope, so there's a slope here, that corresponds to the difference between the control and the treated. And the reason that's the case is R or any other statistical language or kind of linear regression itself is treating control as a number. The number is 0, and treating treated as a number, and that number is 1. So the slope ends up being the difference between the two, and the intercept is the value of the thing that you're comparing it to. So why all of this stuff? So this is where that design formula comes in that I mentioned for DE-Seq 2. Where is that? Here. So this tilde is because what we're doing is regression. We're not doing kind of vanilla linear regression, and that's because we're working with count data. We're doing a special kind of regression called negative binomial regression. Definitely skipping the details of that, but broad strokes, that's what we're doing here. We're performing a regression, but in this case, we don't have a continuous input. We have a categorical input, and that input is conditioned. So R is performing negative binomial regression and comparing, in this case, these two groups, mock and knockdown. The reason, and this approach of using these design formulae, this regression approach, is used for microarray analysis, proteomics, and the reason people do that is this is a very flexible system. So in this case, this is the simplest possible case we have. We just have one input variable, and that's treated or not treated, or mock and knockdown. But what if we had information about, this is cell line data. Yeah, what if we had information, we did this experiment in different cell lines. We could easily add that information as an additional, what's known as a covariate. Maybe it's called cell line. And it can get even fancier. In regression, you can have interaction terms and things like that. So I thought it was worth bringing up the fact that what we're doing here is regression. But in this very specific case, it's identical to just doing a t-test. Yeah.
So with the conditions, you spoke about how there's a slope.
Yes.
Obviously, the x-axis is the conditions.
Yeah.
So what is the distance on the x-axis? Is it because there's rise over run?
Yeah, that's a great question. So I should have maybe drawn that here. So just to restate, in this case, so Paul asked, if you want to have a slope, you have to have a rise over a run. The rise in this case is the difference in the means. And that's pretty clear because our y-axis is numeric. Our x-axis is not. The thing is, this is known as dummy coding. So what R, or linear regression, does is it treats the kind of baseline variable, it gives it a number, 0. So actually, I mentioned this thing called these factor variables. Those are character variables. Those are actually integer variables masquerading as characters. So they're actually just, so when I say control treated, R is just thinking 0, 1. And so it's kind of silly because then it becomes delta y over delta x, but delta x is 1. So it just ends up being the difference in the means.
Thanks.
Oh, yeah, no problem. This, it's silly to say, but this kind of blew my mind when I first learned about this. And I wanted to say, so I have a whole thing here about, again, none of this is really related to RNA-Seq, but it's just about the relationship between t-tests in simple linear regression if you want to confirm to yourself that the output is the same. And there's this wonderful link. Like, I think statistics is objectively difficult, but it's also often, I don't know if it's intentionally taught in a bad way, but this is one of the few resources I've found that explains it in a way that I wish everyone explained statistics. And so here, this line 176, this reference here, I think it's even called like statistics taught right. They give, one of the examples is showing this, how simple linear regression is the same as a two-sample t-test. But then they also go on to just say that everything is linear modeling, ANOVAs, non-parametric, parametric. So this is a really nice write-up. Yeah, and next we're going to dive deeper into DE-Seq 2, including using these additional packages from Bioconductor to kind of derive information, more information about these gene symbols, and then do some visualization. And maybe not next week, but the week after, we can use these inputs to do some more fun stuff like gene set enrichment analysis, pathway analysis, make volcano plots. Yeah, 4 minutes to go. Any questions? Cool. All right. Yeah. Thanks for coming. And again, just let me know if anything was unclear or email me. And if you wanted to see, so I typed a bunch of stuff here just as a reminder. If you wanted to see what the quote unquote answers are, you can just do launch_project, name of the project, and then just do show answers. Why this is not auto-completing equals true, and that should launch. It should. And if you wanted to do launch under, there's also a kind of homework associated with this, and that's just launch_exercise. And similarly, it also has a show answers parameter. And that's if you use this as a reference, you'll be able to answer all the questions in that one. That's just you doing RNA-Seq but using a different data set. Cool. Thank you. Say that again. Oh, I'll come help you with that.